Um, we considered already free vibrations, frequencies, and period and amplitude, sum of two harmonic motions, possibility of detection of aperiodicity, Pythagoras and Hippasus, as told by Plato, and single degree of freedom system. And we are actually now at this single degree of freedom system topic. And what happens here is that we used Newton's law in order to write equation of motion. And this equation of motion looked like this: mu double dot plus ku equals w plus f of t, where w is the weight of this concentrated mass. Then we said we would like to consider to choose a convenient coordinate system. Convenient coordinate system will take into account the static displacement. If there was no dynamics involved, no vibrations, then under static loading, W, the displacement would be W divided by K. So this is a load, that is a stiffness of the spring, and this is a displacement. And then we decided that we will measure our system's displacements around static equilibrium state. Now, static equilibrium state does not exist. It is in our imagination. If this system would have no dynamic behavior, then it would have a static behavior. Then there would be x static. Displacement would be static. But this is just our pure imagination, that there is this x static. This is just a number which equals f divided by k. Or w divided by k is static displacement. So we are talking about vibrations around some level of displacement. And this level of displacement happens to be, it happens that we can find it by static considerations. Now, this is not an artificial matter that we are doing. Why? Because once I substitute this here, I get mx double dot plus x static, second derivative equals 0. Then instead of u, I get x plus u static. Then k times u static is w, and therefore w together with ku static drop. And we are getting actually a simple equation of the motion around static equilibrium state. The static equilibrium does not exist there as such, but vibrations are nice to measure around some value. And this is what is being done. That means the weight can be eliminated in the displacement, okay, of the system if measured relative to the static equilibrium configuration. Okay, we are continuing. Let the displacement of the mass measured relative to the static equilibrium position, x static, is be like this. So I just repeat, then this is an equation. mx double dot plus kx equals f of t. Now, this is our basic equation. This is our basic equation, mx double dot plus kx equals f of t. Now here we can actually make some substitutions. So we divide this equation star by m. We divide this equation by m. So here we will get k divided by m. So instead of the second term, I will get k divided by m. K divided by m I'm denoting as omega n squared. Omega sub n. This n is not number n, but first letter, a letter, English letter n. I'll explain you why this n. Why n, why not m, or p, or q, etc. So I divided this equation by m, I got here x double dot, plus omega n squared, omega sub n squared. So omega sub n depends upon k and depends upon m. It depends upon the mass of the system as well as stiffness of the system. And on the right-hand side, we have this 1 over m times f of t. Now, when f of t is not 0, we call it forced vibration. When f of t equals 0, we call it free vibration. Moreover, we can call this f of t is excitation or loading. Now let us consider this free vibration. Okay, this is an ordinary differential equation, so that is a second derivative with respect to time. And this is a constant times x, constant times function. And we are considering this free vibration. We will consider free vibration. So constant times x. So when I consider free vibration, I would like to do as follows. I will assume that solution is of exponential form. A times e in power RT. Why A in power e in power RT? Because when I differentiate E in power RT, we are getting something that is proportional to itself. So I'm differentiating it, and I'm getting here, look, second derivative will be A times R squared E in power RT. So this R comes every time once and then second time. So I get A R squared E in power RT plus then here omega n squared times A in power RT. Okay, please write down and let us internalize this. Now, A in power RT appears here in the first term and appears in the second term. Why? Because it's nice property of differentiation of E in power RT. So I can take that out of the parentheses. So I will be left with A in power RT times R squared plus omega sub n squared. This equals 0. Now we better write down that A does not equal 0. Because if A were equal to 0, then x equals 0. Okay, x equals A times E in power RT. So if A is 0, then x is 0. But that would mean that there is no vibrations. There is no displacement. But this is against what we say. We say that when system is released or given small kick, system will vibrate. It's very easy to see. So now E in power RT is also not 0. So the only quantity that must be 0 here is R squared plus omega n squared. So that is the only quantity that can equal 0. So that means that I wrote here R squared plus omega sub n squared equals 0. This is called characteristic equation. Now, solution is like this. Let me write down here. When I solve here, omega sub n is a number. If you remember, it equals omega n squared equals k over m. So k is the stiffness of the spring, m is a mass, so they are characteristic of the system. It's a number. So omega sub n is a number. So R12 is plus minus I times omega sub n from here. So because x of t, that means that we have two roots. R1, which is plus I times omega sub n. I equals, of course, square root of minus 1. Okay, and we got it like this. R squared plus omega sub n square equals 0. From here, r square equals minus omega sub n squared. Then r equals plus minus square root of minus omega sub n squared. And this equals plus minus omega sub n squared gives me omega sub n. And here is square root from minus 1, which equals therefore plus minus, this is I omega sub n. Okay? We remember this from various places. However, you may want to write down because things look innocent, but then suddenly we may forget this. Okay, so because x of t equals, therefore, we have two roots, not just one r. We wrote a in power rt, but we have two roots. So therefore, we have a linear combination of solutions. X of t equals a1 in power r1t plus a2 in power r2t. And therefore, because of r1 equals plus I omega n and r2 equals minus I omega n, we get this. X of t equals a1 in power I omega sub nt plus a2 in power minus I omega sub nt. So here it's necessary to remember formula of Leonhard Euler. Who lived between 1707 to 1783. And that is the most famous formula, or one of the most famous formulas in mathematics. In power I alpha, alpha is any real number, equals cosine alpha plus I sine alpha. So it's Euler's formula. So x of t equals a1, therefore, here I have I omega t. Cosine omega sub nt plus I times sine omega sub nt. And when I calculate this, I have cosine omega nt minus I a2 sine omega nt. Okay. If you have any questions, please stop me and ask. So now we see that we have here cosine omega sub nt, and here we have cosine omega sub nt. Here I have sine omega sub nt and sine here. So therefore it makes sense to take out cosine omega sub nt, and then I will have a1 plus a2. So I'm getting like this. X of t equals cosine omega sub nt in parentheses a1 plus a2. Then we have sine omega sub nt. I we are taking out. Is left a1 minus a2. Now naturally that a's are complex numbers. A's, a1 and a2. Because if a1 and a2 were not complex numbers, then suddenly x of t would be a complex. But x of t is a displacement. It cannot be not real. It should be real, x of t. So therefore, this is possible only if a1 and a2 are complex numbers. Okay. So therefore, we denote the combinations of complex numbers. This one, a1 plus a2 equals c1. And this in front of sine omega nt, we not as a C2. Therefore, what we get is x of t equals C1 cosine omega sub nt plus C2 sine omega sub nt. Now, conclusion is as follows. The vertical motion of the block has a vibratory character because cosine omega sub nt and sine omega sub nt are periodic functions which repeat themselves. You see, so this block undergoes harmonic vibration. This block undergoes harmonic vibration. And now, after interval of, now what is a period? Period we know. Now, omega sub n, therefore, is a frequency. Omega sub n is a frequency, circular frequency. So, system vibrates with this frequency. Why sub n? You may ask, why is this index n? Well, it's very simple. Because omega sub n depends, equals k divided by m. K and m are natural characteristics of the system. K is the stiffness of the spring, and m is a mass. So these two are natural characteristics of the system. Therefore, these vibrations are called natural vibrations. And omega sub n is a natural frequency, not just any frequency. Omega sub n is natural frequency, and that is why n. N from word natural. Okay, period equals then 2 pi divided by omega sub n. Or it equals, look, square root. So omega sub n equals square root k over m. So, or if I will write here is m over k, here. Now I will multiply both numerator and denominator by g, which is a gravitation constant. Why do I do that? Because I want to do that. Why do I want to do that? Because I hope I will get something interesting. So I will get then W here. M times G will be W, the weight. Here is kg. So this equals then 2 pi. W over k is static displacement. Now what does it mean, static displacement? A displacement the system would have been displaced had it been statically behaving. It does not behave statically. But had it been statically behaving, then that is what it would be, U static. And this is divided by G. Now, this formula sounds, you may want to write here, paradoxical. Why it is paradoxical? Because we are having vibrations. We don't have static behavior. Suddenly, behavior of vibrations has been expressed in static terms, which is very interesting. Behavior, which is vibrational behavior, that means dynamic behavior, is expressed in terms of static expression, U static. So then we get a rule actually from this. You may say, you know what, in order to find the period, look, this happened, why? In order to find the period, I will just write, I will find the U static displacement, divide by G, and take square root, multiply by 2 pi, I'll get a period. And if I want frequency, I can calculate frequencies then back omega equals 2 pi divided by T. So why this has happened? Oh, this happened because this is not a random coincidence, so to say. This happens because we did rigorous solution of the differential equation. And by this rigorous solution, we got cosine omega nt, sine omega nt, and omega n is square root of k divided by m. And that is why that is how we obtained this expression. So we could not have anticipated this expression from the beginning. If I would have said, think please how much period would be, no one would have said. I mean, at least there is no one who did say in history that is how it will come out. It did come out. Mathematics suddenly was a very nice tool to bring us to this conclusion. Now, this also validates somehow study of statics. You know, when you study mechanics, say in the university, first you study statics, then you study dynamics, then you study strength of material. But there is no such a thing as static behavior of the system. That is an approximation. Everything takes place in time. Okay? Like everything but statics turns out to be a very good approximation, very good model. This model suddenly pops up in unexpected place. You may want to write down. Statics pops up in an unexpected place. That is even, I would say, least expected place, because it pops up in vibrations where there is no statics at all. We can even say, if you want, that world is beautiful. It is designed, I mean, it looks like designed very beautiful, so that things make sense. There is statics, there is dynamics, and they together somehow give us a good understanding of what is happening. Okay, period of vibration, look please. Period of vibration depends only upon the magnitude of the mass and the spring constant. And it is independent of displacement. You see, x of t is not here. Period does not depend on displacement. Means that it can go, it does not depend upon A or C in this particular case, C, C1, C2. There is no C1, C2 there. So therefore it is called natural frequency. Sometimes independence of x is called isochronicity or isochronous. Iso is a Greek word, talks about constant. Okay? Isochronous. So let us summarize what we did up to now. Up to now we have this second order differential equation for free vibrations. So you can put this in the box. mx double dot plus kx equals 0. Omega sub n squared equals k over m. Okay. Then we can also deal with this, some conclusions, very simple conclusions. If the displacement U static is determined theoretically or experimentally, you can say, you know what, it's much easier to determine something that is static. I'll just push the system with, say, unit force and calculate the displacement. Then period can be calculated from t equals 2 pi U static divided by G. And naturally then, so number of natural frequencies, number of reciprocations per unit time, it's also easy. Once I have this, I can find omega sub n. Okay, let us calculate very simple example. So let us imagine mass equals, write down please, mass equals 1/4 of a kilogram. Spring constant equals 0.1533 Newton over millimeter. Determine Bloch's natural frequency in cycles per second. So first of all, a meter contains 100 centimeters, and that means 1,000 millimeters. So therefore, we can write down K equals 153.3 Newton over meter. So F sub n, frequency equals 1 over 2 pi square root K over m. So it's 155 divided m equals 0.25. This equals 3.941 hertz. Hertz is like 1 cycle per second. So very often there are things that are being collapsing because of vibrations. Look please, here we see diameter shaft broken by twisting oscillations, superimposed on high-speed rotation, or valve spring that is collapsing from a motor car engine, or here crankshaft from a motor car engine, etc. Look please here, rotor of aircraft engine, compressor. That is when it was installed, and that is after vibratory collapse. See here. That is a blade failure due to fatigue. Fatigue means time-wise variation of the loading on the system. That is a tanker pipe ridge which broke in 2 parts in 1960. Okay, this is fluid tank subjected to simulate earthquake excitation. Naturally, earthquake excitation is some sort of vibration of the base of the system, etc., etc. So let us consider some mechanical system. So mechanical system would be, you may want to write, this is a beam, that is, we don't see very well here. This is a beam A beam means some structure whose length is much bigger than the dimension of the cross section. Okay. Now the length is L, modulus of elasticity is E. I will just remind you what modulus of elasticity is, because not everyone here is an engineer from hard sciences. So we take this specimen, and specimen we are subjecting by a load, say load P, and cross-sectional area of the specimen is A. Then we divide P over A to find the stress. So that is called stress. Load per unit area. As a result of this load, the specimen elongates. Means that it is not absolutely rigid, therefore it elongates. It's not absolutely rigid. So, but when it elongates, actually, so what happens is like this. Its dimensions become smaller in other direction. So, and then it elongates. So originally there was this length L sub O, original length. Now this is final length. So what happens at elongation, equals final length minus original length. But we are interested, so that is an absolute elongation. Absolute elongation. But then we are interested with relative elongation. And relative elongation is L final minus L original divided by L original. This is non-dimensional quantity. And that is called epsilon. So it's called strain. Bigger the elongations and more strain on this element, of course. So it turns out that there is a relationship. Naturally, this elongation happens because of the load. Load causes stress. So that is here. And it also causes a strain. So very often, or at least in the beginning, relationship is linear. Sigma equals E times epsilon. Okay, at least in the beginning. Say, for example, for the steel, relationship is not like this, but is like this. Okay, so that is what happens. But here, in the beginning at least, relationship is linear in this region. So this relationship is given by this. E is a material constant. and it is called Young's modulus or elastic modulus or elasticity modulus or modulus of elasticity. Okay? That is what E is. So this E naturally is very different from natural basis of natural logarithms that we had when we integrate the differential equation. There it was this E, small e, equals approximately 2, 7, then 1h to 8, 1h to 8, etc. So, but not 5, so a transcendental number. Okay, Euler's constant. So this is something else. This small e is a tool of solving differential equations because this e pops up everywhere, whether he's invited or not. This e has to do with material property. Okay, now, please. So there is, now imagine that this beam, there is this mass that is attached to this beam, mass, concentrated mass. And this mass is such, please write it down, that this mass, attached mass is much, much bigger than the weight of the beam. The mass, so imagine there is machinery there, some big machinery. Okay? So that mass is much bigger than, then I can actually think that this system is very much like what we had before. We can think that whole mass is here, and this acts as a spring. We can visualize that this is a mass, whole mass is here. That means if this is 1,000 kilograms and the weight of this beam is 1 kilogram, imagine. So we can actually say, okay, this whole, forget this 1 kilogram, it is much, much smaller than this. So this is a mass, and this provides actually the stiffness. So that is a spring. So from here we see that we never see in the world 1 degree of freedom system. Mass is put on the spring and it vibrates. There is no such a thing. You will never see. Okay? However, we can approximate real system as mass on the spring. So for example, in this particular case, this concentrated mass on this beam can be thought of as that 1 degree of freedom system that is actually vibrating under the spring. This plays the role of the spring, and this is a mass. Which direction it is vibrating? It vibrates like this. Okay. It vibrates like this. Okay, now let us see, let us think as follows. Let us now we can let us deal with okay. So this system is replaced by this system. Okay, we are forgetting actually this system, and because this we already studied. We solved differential equation. We wrote cosine omega sub nt, etc. Sine omega sub nt. Now I'm saying that this system can be replaced by this system where k natural. Here there is no k. We don't see any k. In this beam we don't see any k. So therefore this k is something that is k equivalent. What is k equivalent? This k equivalent is something that replaces the whole beam on the left-hand side. it is equivalent. This k, the value should be such that what happens is as follows. Look, what is this k equivalent? K equivalent should be such that when in this system there is this load applied, okay, load, then displacement is delta, and their ratio will be k equivalent. Again, what is this k? K is load times display. Load equals k times displacement. K times displacement. So therefore, I will apply here some load. Then I will find the displacement, and I divide load by displacement. This will give me the k. That will be equivalent to the whole beam. Okay. It will be like a representative of the beam. Representative of a beam. This is not unlike, for example, imagine that there is this, say, family is invited to some very big happening. Imagine some feast. But from this family, they have some other engagement. So they do not feel comfortable not to go, not to attend that feast. So they are sending one person from the family to go to that feast. So he is an equivalent representative of everyone in this family. So he represents the whole family for the feast organizers. Okay, something like that. So we are actually forgetting the beam and replacing it by this k equivalent. Okay, now, if this is a beam, those who studied strength of materials and remember, then I'll tell to them that displacement, this is a displacement, under some load P, so please make the picture here of P, equals PL cubed divided by 3I. I'll explain what I is. So those who do not study, that's okay also. They can open Strength of Materials book and find this formula. Those who do not want to go to the library and search for the formula, I gave this formula to you. Now, I is a moment of inertia. You may want to write down what I is. It is a moment of inertia. So moment of inertia actually tells us, let us see here, let us show here. Say, if I imagine this is a beam, so that is a cross section of the beam. Yeah. Can you show us? Can you show us here? Sir, can you show us from here? I would like to demonstrate. So, for example, bending like this is much easier. Bending, okay, like this, much easier than to bend system like this system, to bend this direction. Okay, maybe not so easy to explain here. Okay, if cross-sectional area is like this, then bending is like this, like this way. However, if cross-sectional area stands like this, then bending is more difficult to conduct. So what does that say? It says that, look please, bigger the I, if I is bigger, then delta is smaller. Now what is this moment of inertia? Look please. If cross-sectional area is like this, so that is BH. This is B, this length, and that is H. So moment of inertia equals actually BH cubed divided by 12. Now if I will put this here, so imagine B equals 2 and H equals 10. So then moment of inertia equals 2 times 10 cubed divided by 12 in this case. That's not, that is 20. Also not good. Actually, this equals 2 and this equals 10, because that is bigger than that. So will be, moment of inertia will be 10, 2 cubed divided by 12. But in this case, so this is 2 and that is 10. So moment of inertia is 2 times 10 cubed divided by 12. So this is much, much bigger. Look, please, how much bigger is that? 2, 10 in power 3, 12, and 12 will be cancelling. 10, 2 cubed will be, this is 10 squared, and that is 2 squared. So it's 100 divided by 4. 25 times displacement will be less if I'm putting cross-sectional in this manner. And this can be seen by just simply trying to experiment with quantities like this. So moment is like that, or moment is like this. The same moment is applied. So that is characteristic of the geometry. I is called moment of inertia and characteristic of geometry. Okay, so what I will do is I will load that I will act upon will be mass times g. So mass times g will be the weight of this mass. So I will put here mg L cubed 3 over EI. How much is K equivalent? K equivalent is load mg divided by delta. So when I divide mg by this thing, we'll be getting 3 EI over L cubed. So F sub n equals 1 over 2 pi square root of K equivalent divided by mass. So that equals 1 over 2 pi 3 EI over mL cubed. You see, there are no single degree of freedom systems in the world. But single degree of freedom system is a nice approximation to a real system. It could be a nice approximation of a system. When this will be a nice approximation to a real system? If I have some big mass placed on the massless beam, or a beam with small mass. If I have mass that is pronounced, so this capital